One more thing that we can do with rational functions is that we can try to write a formula for a function that has some specific graph characteristics. Well, let's try it with these three examples. First of all, if we have a vertical asymptote of x equals -1 and an x-intercept at 3, 0, let's think about what that would mean for the function. To get a vertical asymptote at x equals -1, that means that we would have had to have a factor on the bottom in the denominator of x plus 1. We're just picking the factor that would go with this being a 0. So we have to have a factor in the denominator of x plus 1 so that when we put in -1 for x, we get a 0 in the denominator. If we have an x-intercept at 3, that means that we would have to have a matching factor in the numerator, and that would be x minus 3. So now what we know is that we have to have a factor x minus 3 in the numerator and a factor x plus 1 in the denominator. Since that was all the conditions we had for our graph, then this could be our function. There could be lots of other variations of this, but this is one that would work and would give us those two conditions. And we could check this by graphing the function that we came up with. If I graph this function, I should see those two things that I was looking for. I can check and make sure that there's an x-intercept at 3 by using the trace. So that works. And then I can just check for my vertical asymptote behavior. I wanted to have a vertical asymptote at -1. So if I drew in an imaginary vertical line there at x equals -1, I've got the graph going up towards infinity on this side and down towards infinity on that side. So it looks like it works for what I wanted. Now let's try this one. Remember that vertical asymptotes happen at values that make the denominator 0. If we have a vertical asymptote, then we have to have a factor in the denominator that would have that as a 0. This tells me that I would have to have a factor of x minus 2 in the denominator. For my x-intercepts, I have to have a factor in the numerator that would go with that. If my x-intercept is at 0, the factor that goes with that is x minus 0, or I could just make it x. And then for this one, we also want to have a horizontal asymptote of y equals 3. To get a horizontal asymptote that's not y equals 0, that means our numerator and denominator have to have equal degrees. With what we have here, they're already both degree 1, so that works. But now we would have to have the leading coefficients so that when we divided them, we would come out with an answer of 3. If we leave this one as having a leading coefficient of 1, then to get this to be 3, we'd have to make this leading coefficient a 3. So we could just make this 3x over x minus 2. And then we could go back and check and make sure that this works out. So now our leading coefficient here is 3, our leading coefficient here is 1. That means for our horizontal asymptote, we'd have y equals 3 over 1, which is 3, and that's what we wanted. For this one, we're trying to get a hole in the graph at x equals -5. And remember, a hole happens if you have matching factors in the numerator and the denominator, so that this number is a 0 for both the numerator and the denominator. The factor that would go with this would be x plus 5. That means we have to have a factor of x plus 5 in both the numerator and the denominator. That gives us our hole, and then we also want an x-intercept at 1, 0. The factor that would give us that would be x minus 1. To make it an x-intercept, it would have to go in the numerator. We can add that factor to the numerator, and now we have a function that has an x-intercept at 1, because 1 is a 0 for this factor. And since we have matching factors here, -5 would be a 0 of both the numerator and denominator. And that would give us a hole.